Hey guys, I'm back with another JEE problem and a really neat solution. This is question number 8 of set E of JEE Main 2016. An ideal gas undergoes a quasi-static reversible process in which its molar heat capacity C remains constant. If during this process the relation of pressure P and volume V is given by PV to the power n is equal to constant, then n is given by, here Cp and Cv are molar specific heat at constant pressure and constant volume. Now before I describe to you what the question is, let's go over a few terms used in the question. So the first term is ideal gas. What is an ideal gas? The question begins with an ideal gas. An ideal gas is one in which particles have perfectly elastic collisions. Now what is perfectly elastic collision? It's one in which there is no loss of kinetic energy. So if there is no loss of kinetic energy between particles when they collide with each other, then it's an ideal gas. Now what is kinetic energy? It's half mv square. So there is no change in that value. The next term used is quasi-static reversible process. What's a quasi-static process? It happens infinitely slowly. That is, the system is in equilibrium. So let's see what is quasi-static process. Now let's say this is a system and there's a piston here. Now let's say there's a piston here and there are gas molecules, and this system has a certain pressure and a certain volume. Now if I push this piston downwards by an infinitesimally small volume, the change in volume would be dV and change in pressure would be dP, right? So this is very small volume and very small pressure. Now the reason we have quasi-static processes, or theoretically we consider quasi-static processes, is because when we want to draw a pressure volume graph of a certain process, let's say it's at this state right now, A, and then it comes to state B. We want to know how it arrived from A to B, and for that we want to define pressure and volume at each infinitesimally small point, and to do that we will necessarily have to consider quasi-static processes. So that is the reason we consider quasi-static processes, so that we know how pressure and volume are changing or related to each other at every infinitesimally small point. And this place at which the piston rests is known as equilibrium, which it achieves due to whatever is its pressure, and that will decide the volume, and it will rest at this place, and this is known as equilibrium. Right. So now let's see what the question is asking. The question says that the process is given by a relation PV to the power n is equal to constant. Now when PV to the power n is equal to a constant, this kind of process is known as polytropic process. Now a polytropic process is one which follows this expression, this equation, and there can be several cases to a polytropic process. If n is equal to 1, then it's an isothermal process. If n is equal to 1.4 in air, then it can be an adiabatic process. But a polytropic process will always follow this particular equation. And then they also talk about molar heat capacity. What is molar heat capacity C of gas? It is the amount of heat required to increase the temperature of a gas by 1 degree Celsius or 1 degree Kelvin, or 1 mole of gas increase temperature of 1 mole of gas by 1 degree Celsius or 1 degree Kelvin. So that's what molar heat capacity is. And then Cp is the molar heat capacity if the pressure of the system is kept constant, and Cv is the molar heat capacity if the volume is kept constant. And these two values are different, and they are different from C as well. And C is just that we're not trying to put anything constant and just naturally measuring how much heat is required to increase the temperature of a gas by 1 degree Celsius. That is C. Right. So I believe we have discussed everything in the question, And then let's see what they are asking. They are asking if PV to the power n is equal to k, this n is known as polytropic index. Then what would be the value of n? So they have given this n, they have given 4 values or 4 expressions, and we have to find out which is the right expression. Had this been an adiabatic process, this expression would have been right. N is equal to Cp by Cv, but there is no mention of adiabatic process in this question. An adiabatic process is one in which there is no heat loss to the surroundings. That kind of a process is known as adiabatic process. So now let's see how we can solve this question. We will begin by using the molar heat capacity. I just defined it as change in heat over change in temperature. That's the definition of molar heat capacity. So molar heat capacity is given by this expression, dq by dt. How much heat do I need to supply per change in degree Kelvin? And then if there are n moles of gas molecules, I will multiply this expression by n. Nc is equal to dq by dt, right? So this n is different from this n. This n is the polytropic index. This n is polytropic index, or PV to the power n is, this n is different. This is polytropic index, and this is number of moles. So we will try and differentiate between these two n's, or I will substitute this polytropic index n as z in further discussions. So or rather, let me first tell you the shortcut method to solve this question, and then I will come and try to describe you this question in further detail. So I was planning to do it differently, but it just occurred to me that I'll first just tell you the solution. So for a polytropic index, the relation between C and Cv is given by this expression right here. C is equal to Cv plus R upon 1 minus Z, where R is the universal gas constant. You must have heard of it, which is equal to the Boltzmann's constant. So R is that. C is the molar heat capacity. Cv is the molar heat capacity at constant volume. So this expression you can memorize. It will be useful for you in solving other questions of JEE as well, since they have introduced polytropic processes into JEE. So this is the expression, and then you can solve it by using Mayer's equation. Mayer's equation, which I'll discuss further in the later section of this video, that is given by R is equal to Cp minus Cv. So this gives the relation between R, Cp and Cv. So if I substitute instead of R, if I write Cp minus Cv, I will get this expression. So that is C is equal to Cv plus Cp minus Cv upon 1 minus N. I have written N and Z, but these are the same values. I was just telling you I am going to substitute N for Z, but they are the same thing, polytropic index. Now if I put this Cv or send this Cv to the left hand side, I get C minus Cv is equal to Cp minus Cv over 1 minus N, right? So now C minus Cv is equal to Cp minus Cv over 1 minus N. I will cross multiply, send this 1 minus N here, and I'll get 1 minus N is equal to Cp minus Cv over C minus Cv, right? Where Cp is molar heat capacity at constant pressure and Cv is at constant volume. Now what I can do is I can send this N over to the right hand side and send this entire expression over to the left hand side. That will give me, and then I can interchange. So that will give me N is equal to 1 minus Cp minus Cv over C minus Cv. I hope this is clear. And then if I take LCM, this is just simple maths. You can try yourself by any way you you are usually used to. So if I multiply this C minus CV to 1, I will get C minus CV and then the minus expression, and if I remove these brackets or send this negative expression into this bracket, I will get minus CP, and then minus of minus CV is positive CV. So this is what I will get, and then C minus CV is now the LCM since I have multiplied 1 with the denominator, right? So CV and this CV will cancel out. Minus CV plus CV is 0, and what I will be left with is N is equal to C minus CP over C minus CV, which is the option number 3, and that is the right answer. So this is how you can solve the question in short. But in case you are wondering how did we arrive at this expression, so I am going to derive and I am going to show you how did we come to this expression, and then after that I will also discuss this expression right here. How can we derive this expression? So let's go over to the derivation of the expression that I've just shown, which is unique to polytropic process. So let's see. By definition, molar heat capacity is dq by dt, change in heat over change in temperature. So it's the amount of heat you need to supply to bring about 1 degree Celsius change in temperature. And then if there are n moles of gas, I can write NC is equal to dq by dt. Now if I send dt to the left hand side, I will get this expression right here. NC is equal to dq by dt, and then NC dt is equal to, I have sent dt to the left hand side, is equal to, what is dq? If we look at the first law of thermodynamics, we get delta U, that is change in internal energy. This is the internal energy, this is the heat of the system, this is the work done by system, right? So the first law says delta U is equal to heat supplied minus the work done by system, right? And then work done by system is given by the formula pressure times change in volume. So the pressure on this piston right here, and then pressure is force multiplied by area, force divided by area, and then multiplied by the volume. So that change in volume, that will give me the work done. So I have substituted, instead of writing a dq, I can write du plus pdv, which I get from this expression. If I keep q here and send w to the left hand side, I will get q is equal to delta u plus w. So instead of delta u, since I am talking about a small change, I can write du. Delta u is big change or a larger value, and du is a very small value. In this case, infinitesimally small value, since we are considering a quasi-static process. So du plus, and then instead of work done, I can write pdv, right? And then I will try to integrate this so that I can get the real values, not just infinitesimally small values, right? So let me integrate these two sides of the expression. The way I can integrate is, if I put integral signs throughout, and then I know that number of moles is not going to change, n is constant, and we know that the constant is not integrated, you can take it out of the integral sign, right? So this n can go out. Molar heat specific capacity is also constant for a gas, so these two will not be integrated, these are just constants. And then the integral of dt, you can just integrate dt is t, right? Or I can say that change in temperature, delta t, so integral of dt is delta t. And then on this side, what will be the case? Same, n and cv are constant, right? At constant volume it will have a constant molar specific heat, so these two can come out, and then dt, integral of dt is t or delta t. And then integral of pdv of, now integral of pdv I'm going to write as pv to the power z upon v to the power z. This z is polytropic index, and just to differentiate it from this n, I have written it as z, but in this question it's given as pv to the power n. And since I want to utilize this expression, pv to the power n is equal to constant, I am going to multiply it in the numerator and the denominator, so it won't make any difference. I can cancel these two values out and get the above expression. So but right now I'm going to multiply it in the numerator and the denominator, right? So I can take this PV to the power Z, this I know it is constant, I can take it out of the integral sign. So in the next part I'm going to leave these parts as it is, as they are, and then I'm going to solve for this integral. And let me show you how we can integrate PV to the power Z upon V to the power Z multiplied by dV. So PV to the power Z is given in the question as constant. We will take this out and then integrate V to the power minus Z. Now V to the power minus Z dV, you know the general expression for integration for an expression x to the power n dx is just x to the power n plus 1 upon n plus 1. So using this formula, this is a very basic integration formula, we can find V to the power 1 over V to the power Z as, I can write 1 over V to the power Z as V to the power minus Z, right? The exponent will be minus Z, and then I can use this formula to write V to the power minus Z plus 1 over minus Z plus 1, right? And then I should have also told you that I am trying to integrate from its initial volume to its final volume. So I will write Vi here and Vf here. And the way to solve this expression is PV to the power Z multiplied by V final minus Z plus 1 over minus Z plus 1 minus V initial minus Z plus 1 over minus Z plus 1, right? So V is the variable here, right? V is the variable here, Z is a constant. So instead of V, I can substitute V final and V initial. That's how we solve such expressions. So I will subtract these two. Now what's next? PV to the power Z, V final minus Z plus 1 minus, since the denominators are same, I can write minus V initial minus Z plus 1 over minus Z plus 1, right? Now we also know that for this process, polytropic process, Pi Vi is always constant. So I can say P initial V initial to the power Z is equal to P final V final to the power Z. It does not change this for a polytropic process. So I can substitute this PV. Once I will write, instead of PVZ, as P final V final to multiply it with this expression so that the exponents can cancel out. And then the next time I will use Pi Vi to multiply it with this expression right here, so that again exponents can cancel out. So what happens when I multiply these two? When I multiply these two, PVZ multiplied by V PVFZ multiplied by V minus Z plus 1, you can add the exponents since V final is the same, right? The base is the same. So Z minus Z will be 0 and you will get PFVF minus PIVI multiplied by Vi will give you Pi multiplied by Vi Z minus Z plus 1. So again Z minus Z will cancel out and you will be left with PIVI. I hope this makes sense. If it does not, let me know in the comment section and I will explain to you. It's just simple maths, right? So what is PFVF minus PIVI over minus Z plus 1? We know that PV is equal to nRT. This is the ideal gas equation, right? PV is equal to nRT right here. So I can substitute PFVF as N times R times T final, that's the final temperature of the system, minus N times R times T initial, right, over minus Z plus 1, but I'm not going to write that right here, right? So, or I have already written it here, right? So NR, now N and R are always constant. So R is universal gas constant, number of moles is not going to change since it's a closed system. So NR can be taken out as common, and what we will be left with is TF minus TI, which is delta T, right? Delta T is change in temperature, which is T final minus T initial over minus Z plus 1. Now I have this value. I started with solving the integral part of this equation, so I am going to substitute the integral part right here with this value I just found. This value, if I substitute this, I will get NC delta T plus NCV delta T plus NR delta T over minus Z plus 1. Now you can cancel out N here. You can take N common from this expression, that will cancel out. Delta T will also cancel out. You can take delta T common from right hand side and you can cancel this. So what you are left with, what we began to try and derive, the expression that we wanted to derive, which is this expression, C is equal to CV plus R over 1 minus Z. So this is how we got C is equal to CV plus R over 1 minus Z right here. This is what we wanted to derive. I thought it will be a good idea to show you how we got this expression, which describes the relation between C, CV and R in a polytropic process. Right now, during this solution, earlier solution, I substituted R as Cp minus Cv. Now I'm going to show you, this is known as Mayer's equation, M-E-Y-E-R. I'm going to show you how you can derive the Mayer's equation as well, because this will give you a strong foundation for solving IIT JEE questions. So let's see how we can derive Mayer's equation. So let's say H is equal to U plus PV, where H is the enthalpy, U is the internal energy, and PV is the work done, pressure times volume. This is the basic expression for enthalpy. If you have not heard of it, then you can go through it in your NCERT book. And then let's differentiate it to get DH is equal to DU plus D times PV, right? So what is DH? Change in enthalpy. Again, we will use the same equation that we have been using, which is NCT is equal to NCV dt plus dNRT. PV is equal to nRT is the ideal gas equation. Change in internal energy is also given by this formula, NCV dt, and change in enthalpy is also given by this formula, number of moles of gas multiplied by molar heat capacity at constant pressure multiplied by change in temperature, right? So that's what enthalpy is. So you may wonder why we have used Cp here and why we have used Cv here. The reason is enthalpy by definition is heat absorbed or given away at constant pressure. Since enthalpy is defined at constant pressure, I am going to take Cp, which is molar heat capacity at constant pressure, and then I am going to take molar heat capacity at constant volume for delta U, because delta U by definition, or change in internal energy by definition, is heat absorbed or given away at constant volume, right? So that's why molar heat capacity is taken as Cv in this expression. Now R is a constant, right? So N is also a constant, so I can take these out of differential. Constants are not differentiated, so NR can come here and then I get dt. Similarly to how we previously cancelled out, in this case too, N and dt will cancel out, and you will be left with Mayer's equation, which is Cp is equal to Cv plus R, or Cp minus Cv is equal to R, which we used in our solution right here. So this is how you solve for the Mayer's equation, or you derive the Mayer's equation. I hope this was you like this solution and this was helpful to you. If it was helpful to you, please like and subscribe, and share it with your friends. I put in a lot of hard work to solve these questions, and please also comment below. Thank you for watching.